Hello everybody, this is Trevor Smithy, and welcome to the first official dev diary for my latest project, a MIDI-based rhythm game. As my first real video game, I've got plenty of ideas and features I want to include, but for now, let's get right into it. For this first dev diary, I thought it would be a good idea to cover what exactly MIDI is. MIDI, which stands for Musical Instrument Digital Interface, is, as its name implies, a communication standard and file format used for connecting electronic instruments, samplers, and computers together. Unlike many other audio formats such as MP3, WAV, and OGG, MIDI works with discrete notes and sound fonts instead of actual audio waveforms. This allows MIDI the ability to do many things that other formats can't do, or at least not as easily, such as swapping instruments, changing tempo or pitch, and editing on the fly. For now, I won't cover why I believe MIDI's capabilities in these regards will be crucial to implementing the features I've imagined, but rest assured that will be explored in future dev diaries. You may be wondering, well then, if MIDI doesn't store audio waves, how does it work? How can a relatively small file encode such a versatile set of instruments, features, and more? And how would you even go about making a game using it? Well, if you are wondering that, then hopefully this video is for you. MIDI files, denoted by the .mid file extension, are simply just a series of 8-bit bytes. Each of these bits is a 1 or a 0, with each following byte representing twice the value of the previous. This means each byte can represent any value between 0 and 255. Throughout this video, I will often refer to these bytes in their hexadecimal form. Hexadecimal is often used with computers as it is more compact than binary or decimal due to being base 16, while working nicely with the base 2 nature of computers. Each byte can therefore be represented with just 2 hex characters. The bytes in MIDI files are always contained within one of 2 types of chunks, header chunks and track chunks. Let's cover the header chunk first. Each MIDI file has exactly one header chunk at the beginning of the file, and is then followed by one or more track chunks. The header chunk can be broken down into 5 main sections. First, we have the chunk identifier. For the header chunk, this is always the ASCII representation of the 4 ASCII characters uppercase M, uppercase T, lowercase h, lowercase d. In the example here, you can see that in hexadecimal this is represented as hex 4D, 54, 68, 64. Second, we have the length of the remainder of the chunk. This length value is assigned 4 bytes. However, since the header chunk only has 6 bytes left, only the last length byte is used, and is always assigned the value of 6. Third, we have the format of the file, which is assigned 2 bytes. There are only 3 valid formats in the current MIDI standard, Type 0, Type 1, and Type 2, represented as hex 00, 01, and 02, respectively. Type 0 files contain only 1 track, Type 1 files contain multiple simultaneous tracks, and Type 2 files contain multiple sequential tracks. For the purpose of this project, I'm only planning on supporting Type 0 and maybe eventually Type 1 files. Fourth, we have the number of tracks, which is also assigned 2 bytes. For a Type 0 file, this will always be hex 01. The maximum number of tracks is 65,535. Finally, we have the division of the file, which is assigned the last 2 bytes of the header. This value represents how many delta time ticks are within a quarter note. I'll cover delta time and ticks in more detail later. To review, a MIDI file has exactly 1 header chunk at the beginning of the file. It consists of 4 bytes for the header text, 4 bytes for the length parameter, 2 for the format type, 2 for the number of tracks, and 2 for the number of ticks in a quarter note. Following the header chunk, there will be 1 or more track chunks, depending on the format type. Like the header chunk, each track chunk starts with a 4-letter chunk identifier, in this case the ASCII characters uppercase M, uppercase T, lowercase r, lowercase k, which looks like hex 4D, 54, 72, 6b. Also like the header chunk, the next 4 bytes are assigned to the length of the chunk. In this example, there are 196 track bytes, so it is hex C4. After this, however, is where it can start to get a little bit more complicated, so I'll do my best to simplify. Following the length parameter, a track chunk is made up of a series of track events, which consist of a delta time and the event itself. Okay, so what is delta time? Delta time is simply the number of ticks since the last event. Ticks are small units of time between each note. In the example, our file has a division of 192 ticks per quarter note, so if a note lasts for a whole note, then it will have a delta time of 4 times 192, or 768 ticks. However, delta time is not stored directly as a series of bytes. Instead, delta time is stored as a variable length quantity. So what is a variable length quantity? Well, instead of having a set number of bytes to represent the length of a value, VLQ uses the highest bit as a check of sorts to see if the current byte is the last byte of the value or not. Long story short, this means that a bit of extra math has to be done in the background to ensure a correct delta time is calculated, but with the benefit of having a flexible system that doesn't waste bytes if a delta time is too short, or is incapable of handling longer delta times due to a lack of assignable bytes. I apologize if that was hard to follow, but thankfully understanding VLQ doesn't matter unless you're directly dealing with raw MIDI files. Just know that whenever I mention them, it's because I went through a bit of trouble trying to wrap my head around them. Returning to where we were before, the second part of a track event is the event itself. These events can be broken down into two main categories, meta events and standard events. Meta events consist of non-musical functions such as setting the sequence number, defining a text event, track name, instrument name, tempo, time signature, key signature, and most importantly, designating the end of the track. I'll cover these in more detail when we break down the example file. Standard events are the bread and butter of MIDI. These are the most common and include turning on and off notes, changing the pitch, changing the instrument, pressing a pedal, and more. Let's look now at the example file. As you can see here on the left, I've displayed the file contents in hexadecimal, which won't be all that helpful, but is important to understand how things are arranged. On the bottom left, you can see the header chunk information. The only thing of note here is the value of 192 ticks per quarter note, which will be helpful when looking at the delta time of events to determine the note lengths. On the right, you'll see what I spent the most time on, the track reader. This reads the track chunk and translates it into a much more understandable format for humans, and will be the primary focus for the rest of the video. At the top of the track reader, you'll see the length of the track, which is 196 bytes. As mentioned before, this is represented by the hex 000C4 in the file. Following the length, we have a delta time value of 0, followed by a hex FF in the file. Hex FF is shorthand for a meta event. The next byte, in this case hex 58, identifies this as a time signature event. Meta events, like the header chunk and track chunk, are followed by a length byte, in this case 4, meaning the next 4 bytes are part of this event. The first byte represents the numerator of the time signature, in this case 4. The second byte represents the denominator as a negative power of 2 for some reason. In this case, this results in 4. The third byte is the number of MIDI clocks per metronome click, which is 24 in this case. The fourth byte represents the number of 30-second notes in a quarter note, which is 8 here. So all of this means is that we have a standard 4/4 time signature. Next, we again have a delta time of 0 followed by hex FF. This next byte, hex 51, shows that this is a meta tempo event. Tempo events are one of the few multi-byte values that is not stored as variable length quantity, and instead has a fixed length of 3 bytes. The 3 bytes in this example are hex 0A, E6, and 2D. This results in a value of 714,285. You may be wondering, why is the tempo set as such a high value? Well, that's because it's not represented as beats per minute, but rather microseconds per beat. This allows for a great degree of decimal precision, allowing for non-integer tempos. In this case, however, the tempo comes out to a clean 84 beats per minute. Following this, we have a few more meta events at delta time 0, a track name event denoted by hex FF3, and a text event denoted by hex FF1. Something I glossed over before is that each track actually has 16 separate channels or instruments that it can contain. In hexadecimal, these channels are represented as the second character in the byte, with 0 being the first channel, 1 being the second, up to F being the 16th. This is relevant because our next event is a program change event, which is denoted by hex C followed by the channel, which is in this case 0. This event sets the instrument to be used, in this case instrument 9, which is a glockenspiel for channel 0. Next, we have arrived at the first note of the song. Our current time is still at 0, but that will soon change. Note on events are designated with hex 9 followed by the channel number, again in this case 0. The next 2 bytes are part of this event. The first byte is the key number. Hex 51 here represents the equivalent of a 5th lowest A on a piano, or A5 for short. The next byte is the velocity, or volume, of the key. Hex 64 here is 100 in decimal, which is the volume out of a max of 127. Our next event finally has a non-zero delta time, in this case 192 ticks, which as established before is the length of a quarter note in this example. Here we have another note on event, this time G5 at a volume of 100. With the next event having a delta time of 0, it takes place at the same time as the previous event. Here we see our first note off event, which is identical to the note on event with the distinction of using hex 8 followed by the channel number instead of 9, with a volume of 0. In this case, the event simply ends the first note that we played. In this example, this pattern repeats, playing a new note, each quarter note, alongside stopping the previous one. Finally, at the very end, we have a longer delta time for the last event. As denoted by the hex FF, this is a meta event, specifically the end of track event, designated by the hex 2F followed by 0. Now you may be wondering, what does this even sound like? Well, unfortunately, I haven't implemented playback into the program quite yet, so we'll have to use a separate program to listen to it. Here, I'm using the free MIDI editor, which I'll leave a link to in the description. If you plan on inspecting and editing MIDI files, I highly recommend it. If you're interested in the project, I recommend subscribing and turning on notifications to learn when I post my next dev diary. You're also welcome to join my Discord, which will be linked in the description. Depending on when you watch this video, there may also be other links in the description to support me or even try the demo when I publish it. Thank you so much for watching, and as always, wabam!